We are there into the course curriculum where we are trying to now make in hybrid systems that solve problem, and the first of all which is of course a very exciting system which are known as the evolutionary neural networks. We were there discussing in how can we evolve a variable architecture neural network. We were right there into that kind of a discussion, and today of course, some part of analysis of the variable architecture neural network is left. What we'll see immediately after this heading that I have touched upon, some of which I have already written down on the board, and that states how do we carry out an evolution of neural network using grammatical evolution. So this is what is the grammatical evolution of the neural network. Now for now, let me say that in totality, what a neural network is just a mathematical expression. It is just a kind of mathematical expression. I give you any neural network, you will be of course able to write down a big hefty mathematical equation, an equation that solves that neural network. This one particular equation, no matter how long it be, it will take in all the inputs that are given to your system. It will take in all those inputs that are given to your system. It will carry forward some kind of processing of these inputs, and it will produce an output. So this entire hefty equation is what we are trying to do using grammatical evolution. Now again, let me repeat that grammatical evolution has its base from the evolutionary programming, from the genetic programming. In fact, it is nothing but a linear representation of individual in genetic programming that is able to evolve out a program. We've seen out in the earlier lectures in how this kind of programming tool evolves an equation. We've seen how it evolves an equation altogether, and that is all exactly what we are going to do out over here, where we would be trying to evolve out an equation, and that is the equation of the neural network. And since it is the equation of the neural network, we need to be very assured about one thing, that it obeys the general architecture, the laws of the neural network. So here we would be dealing with this task, and again, as we've seen multiple times in the entire discussion of evolutionary neural network, we'll take the ANN part as conventional, we'll take it as a problem of evolutionary algorithm, and in this case the grammatical evolution. We'll take the evolution of neural network as a standard problem of grammatical evolution, and then is how we would be seeing that how we can solve this problem which is given to the grammatical evolution to solve. So first of all, that whenever I need to deal with any standard problem of grammatical evolution, the first thing that I need to carry out is to make the grammar. Once I have my grammar ready, everything else becomes on the same lines of problem solving with grammatical evolution, wherein based on this grammar I'll be able to generate some random set of individuals as my initial population. I will be able to make some stopping criterion based on the best fitness, based on anything. I would further be able to, using the same techniques, be able to carry out some kind of operations on this population pool, so that the higher generation is better than the previous generation. And because the representation is linear in case of grammatical evolution, I'll be able to carry all my conventional genetic operators, and of course I'll be able to find out the fitness. That is a normal fitness when we measure in terms of ANN, that is where the fusion of ANN and the problem happens to be. So all I have to do is that I have to mainly write down a grammar that is able to evolve this equation, its equation of the neural networks. So again, my grammar is nothing but it's a set of terminating expressions, a set of non-terminating expressions, a set of rules, and a start symbol. As we saw in any grammatical evolution problem, this is the set that defines the grammar. I'll deal with one of them one by one. first come the set of terminating expressions. Now I know that in this entire equation that I have got, will be nothing but a sequence of digits. The sequence of digits is nothing but numbers. So there will be some numbers. 123 can be 1, 2, followed by 3, 98 can be 9, followed by 8. So there will be some number. Of course, if it's we talk about numbers in the entire problem solving that we done, we always normalize inputs and outputs between 0 to 1. So the weights also lie between 0 to 1. So there will be some decimal points in these numbers, followed by some inputs. And let me say that my system has n inputs, so there are exactly n inputs over here. So it's nothing but a sequence of numbers, those what represents the weights and the biases in our final equation, and these numbers over inputs over here. Now we've not written down two things over here. We haven't written down a decimal point because in this grammar I do not regard it as a symbol. I regard it as something that I would be normally drawing in my entire list of that I'll be using it conventionally in my rules. So I have not regarded that as a symbol. And the activation function, that I have again assumed that some activation function, let it be some capital F. I am not specified F over here because I will not be using this as a symbol in my program. I will be writing down in the rules as it is. It would become a symbol in case some rule can operate over this, or it can be resultant output of some rules which I will not be taking out in this case. So I will not regard them as a symbol, but all the other things have been listed out over the set of terminating symbols that my final equation that I get will have. And the set of non-terminating symbol, that this is exactly as per you model your grammar. So if you repeat my lecture into what neural network is, what are its basics, what are its constituent parts, any term that I used over there has been written down over here. Any term that I probably use has been written down over here. So now my task is only that whatever I told as rules in the earlier lectures, I have to formally write it down using a BNF or a Backus NOR form. Whatever was verbally told, that there would be some neurons in a layered architecture, it would take some inputs, it would do some kind of processing, those outputs will become the input of some other input neurons. Only thing is that these needs to be written down in formal form, and those are in form of rules that we write down over here. So these are the non-terminating system. As per this, a starting symbol is always the A and N. That is what I will see later. The starting symbol is always A and N. That's the artificial numerator. That is what I will see in later, because all rules have been evolved from this A and N. So the thing now that remains is that I need to write down the rules. The only thing that I have to do in evolving out this neural network is to write down some form of rules. And when I write down these form of these rules, all my work would get over as far as the specification of grammar is concerned. So how is it that in the system I am able to write down some format of rules? We look at these rules out over here. We'll start up right from the top of a hierarchy where we have a very broad look at the entire neural network, and we'll keep on going lower and lower into the hierarchy. So we start off with nothing but the start symbol itself. We start with the ANN. And ANN is nothing but a collection of neurons. And ANN is nothing but it is a collection of neurons. What I mean by a collection of neurons, that let me say this was the architecture of the ANN, the inputs, the hidden layer, some outputs, and an output over here. Let me say that this was the way architecture out over here. So an ANN is nothing but a collection of these neurons over here. Now the input layer is always fixed, the output layer is always fixed. When we talk about any evolution neural network, the inputs and the outputs are always fixed in nature. So all I have to do is that I need to change in these number of neurons, add them down, reduce them down, have more and more neurons, have lesser and lesser neurons, or whatever. This is the only thing that I need to specify in an ANN at the broader level. Of course, at the lower level there are weights and biases, but at the broader level, this is the only thing that I need to specify. So I say that ANN is nothing but it's a collection of neurons. So probably this much is an ANN, this is another ANN, this is another ANN, this itself can be an ANN, a collection of neurons. So everything that an ANN is a collection of neurons. How do I operate on this collection? I say that ANN in its Backus knot form is either a neuron or neuron followed by an ANN. It's either neuron or neuron followed by an ANN. Any ANN can be regarded, any neuron can be regarded as an ANN, or I can have an ANN and a neuron added over top of it. So this is what the rule of ANN says, and there is no other means that I can make an ANN. So there are only two conditions out over here separated by this DNF, or it's either a neuron or a neuron followed by an ANN. If I say anything, a neuron, ANN, neuron, that will be equivalent to 2 times application of this thing. If I say it's ANN and neuron, that will again be the same architecture, so it does not matter. These are the only two ways that I can make up a higher order ANN from a lower order ANN. And that is what is the basics of the grammatical evolution. Whenever I make this grammar, I take up every non-terminating symbol. In this case, starting from the highest order to the lowest order, I take in every non-terminating symbol and I see how is it that it can be formulated from its just lower constituents in terms of abstraction or itself in its abstraction. So in this case, an ANN was nothing but a simple neuron or a neuron added to an ANN. Now the key element is that what is ultimately a neuron. So I reduce the level of abstraction by 1. I go lower to the abstraction and I see what ultimately a neuron is. I see ultimately what a neuron is. And again, what I had covered in the initial neural networks, way before we started, where we were dealing with perceptron and all these things, a neuron is nothing but a basic constituent element that does some basic processing. That is what does the most basic kind of processing. That is what the neuron is. So when I am talking about neuron, I will be talking about processing. Processing is of two parts. Firstly, the summation part, and secondly, the integration part. So a neuron is nothing that will first carry forward the summation and then carry forward an activation function F. And that is exactly what I write. Let the summation be known as a weight. I mean, this entire summation is modified by some weight. I have W1 over here, W2 over here, W3 over here, I1 over here, I2 over here, I3 over here. So it is a vector weight. It is a vector weight multiplied by some and a bias, and an activation function applied over it. The neuron does nothing but, if we consider only this part, I have been a little wrong in how I interpret this weight. So this is not the same weight that we are talking about. This is not at all the same weight that we were talking about over here. So there is a little bit of wrong delivery on my part. So what a neural network does, a neuron does is nothing but a summation part over here and an activation function applied over here. The summation part, when we talk about, whenever we talk about the summation part of it, it is of the inputs as well as the bias. the summation part is of inputs as well as the bias, because what we saw earlier is that output of any neuron is summation wi I equals to 1 to n plus bi plus a bias. So this is what is the summation part, this is the bias part. So that is what I have done. If you look at only this part of this neuron, it consists of a summation part and a bias part. Bias, for that sake, is nothing but a simple number. Bias would be nothing but a simple number, and sum would be a very simple summation over weights and inputs. So that's what I've done. This is what sum happens to be. This is exactly what sum happens to be. That is some weight vector multiplied by the input list. And the bias is nothing but, it's a number. So bias is simply a number. What this is all about, the sum is the weight multiplied by some kinds of inputs. And again, remember that I am talking about the evolution of the entire equation of the neural network. So what this I am dealing about is that can I evolve the complete equation that finally the neural network presents. So this is what the sum is, that when I apply weight to the input, so it will be some weights when multiplied over the entire input list. Input list is the input data given to the system. So if I have a 3-layer architecture of the neural network like this, where there is an input hidden and an output layer consisting of only one neuron out over here, if there is this type of architecture, what this neuron in this part does is that any neuron takes its inputs, multiplies them by the weights, and take an activation over it, and take some kind of activation over it. So that is what it has done. It has taken some kind of some part of it, and it has taken some bias to it, and it has taken the activation part of it. The output will go in and for another weight. This will be whatever weight this represents out over here. So it will be ultimately applied to another kind of weight, and this is the weight that I have out over here. So what a neuron in this layer architecture represents is that it represents this complete thing. It will represent this complete thing where I'll have multiple neurons out over here. It will represent whatever inputs it takes, those are the standard system inputs. It multiplies them by some weights. It multiplies them by some weights. After that, it does some kind of adds some kind of bias. That is what happens here. When it multiplies the inputs by the weights, and it adds a bias over out here, it passes over the activation function, and this weight it multiplies. And that is how I get a part of the system output as my neuronal output. That is what I have as my neuronal output. So I guess this is done. So still lower down into the hierarchy, still moving down a bit lower into what the layer abstraction was. Now I am almost done. I said what an ANN is: a collection of neurons which had two rules, either a neuron itself or a neuron added over on top of existing ANN. I said that neuron was nothing but what connects the input layer to the output layer. So it had some weights multiplied by the applied system inputs, that is the input list, it done some kind of submission, it added the bias, it passed it over to the activation function and multiplied it by the output vector weight, multiplied it by the weight of the output neuron. So that is what was my weight, my activation function, my sum and my bias. Of course, if it's a sum, I'll add it over to the other sum. The sum I can generate it by two ways. I can generate it by two ways. Either I split it across into two. I say sum is nothing but a summation of two sums. Or I say it is weight into input list. Now, what would eventually happen out? Why do I need these two sums? Suppose that what I was trying to generate was I1 W1 plus I2 W2 plus I3 W3. Now, I'll start off with one sum. I'll split it across two. It will become sum plus sum. But I need three sums. So I'll again split it across two. I'll say it is sum. The first sum I'll split it across into two. So it will be sum plus sum plus sum. Now I'll say that the first sum is weight into input list, the second sum is again weight into input list, the third sum is again weight into input list, and the first sum, weight is nothing but the number and input list is any one input. Input list is any one input of this entire system. So out here, what is ultimately happening is that I am generating in using this concept of sum, what I am generating in, I am generating expressions like W1 I1 plus W3 I3 plus W5 I5, or let me say in another case W2 I2 plus W1 I1, or in another case W1 I1 plus W6 I6. That is what I am trying to generate out when I take out this concept of sum. Weights are any real numbers, so I can expand in the notion of weight to any way. I can expand the notion of weight to any way that I like. They are just simple numbers. Of course, W1, W2, W6 are not terminating, they are not defined. I'll have to key in some numbers, and that is what it has its own pool of generation that it can adopt. That is what the weight is. And what the input list is any one input. So that is what I specified over here. Input list is any one input out over here, out of this entire number. And in the next level of abstraction, I got in a definition of weight. Now this is the entire thing is nothing but how do I evolve in a number in this system. Others are done. These are terminating. All these are terminating. So all I have to do is to generate some kind of mechanism by which I can generate a number, because weight is just a number, and this is the mechanism I use to generate the numbers. Again, I said that still lower down into abstraction. Now I've gone way far from the neural network. I've penetrated deep inside into how do I generate a number in the GP. That is what the abstraction that I am dealing with now. How do I generate a number in genetic programming, or in this case in grammatical evolution, how do I write down these rules? A number is nothing but positive list of number or a negative list of number. It has three parts. The first part is the sign. It can be positive or negative. The second part is what follows before the decimal, and third part is what follows after the decimal. So it's 1, 2 and 3. Based on this, I have written down how do I generate a positive number and how do I generate a negative number. That's what I have written down. And a number, a digit list here. A digit list here is what I need to generate. So this can be 123.769. So 123 I need to generate here and 769 I need to generate here. It is nothing but a sequence of numbers. A sequence I can define it by as either just a digit or its digit followed by a digit. That is what digit list is defined. Either just one digit or a digit followed by another digit. And a digit is again all set of terminating numbers from 0 to 9. So I started a way across in my hierarchy where I was dealing with the complete AN, and I said that it's nothing but a sequence of neurons. So the entire discussion that I do with a sequence of digits is exactly the same as I did with my sequence of neuron. There were two ways in which I could generate a sequence of neurons or the ANN, and similarly there are two ways that I can generate in sequence of digits or my number. A digit list is a digit followed by a digit list or digit, and of course the digit list can be positive or negative, so we put an addition rule for number over here. So that is how generation of numbers is. So from ANN we move to neuron, from neuron we move to weights, from weights we move to numbers that are real numbers, either positive or negative, and that is what the complete grammar is. We talked about the terminating symbol, non-terminating system symbols, set of rules, and a set of start symbol. Now, very quickly, a very short example. We're starting with something known as ANN. Let me say an ANN is represented like this. And input I1 here and input I2 over here. Let me say 0.5 weight over here, 0.1 weight over here, 0.7 weight over here, and 1 weight over here. This was with a bias of 0, this was with a bias of 1. A weight of 0.2 over here and a weight of 0.2 over here, and this is what my system output. So the resultant equation would come out to be, let me say, I1 into 0.5 plus what this neuron gets, 0.7 into I2. The input neurons do not have bias out here, so there will be a 0 bias over here, 0 bias, plus the bias 0 out over here. Multiplied by the activation function. This is what this neuron will produce as its output. This is what this neuron will produce as its output. Similarly, the other neuron, the second neuron, I have got only two neurons out over here. What it will produce as an output would be I1 into this weight, that is 0.1, plus 1 into the second weight, I2. Let me say this is 1.0, plus the bias 1 out over here. The bias, so it's the first input multiplied by its weight, second input multiplied by its weight, plus the bias and activation function out over here. So I got output of these two. I got the output of these two neurons. All I need to do is produce the output neuron. So it's 0.2 times the first output and 0.2 times the second output. And if I sum these two up, I get what becomes the summation part of the output neuron. Let me say that it had a linear activation function, so that becomes the output code. The only thing is that using that grammar, using the same grammar, can I evolve this kind of neural network? Using the same grammar that we discussed, can we generate in this kind of neural network? That is what I am basically supposed to do. That is what I am supposed to carry out. We always started with an ANN. So I start off with my ANN in step 1. I say step 2, I decompose to ANN as ANN plus neuron. Step 3, I decompose this ANN to neuron. Here I had applied the rule for generation of ANN, where an ANN was split into ANN plus neuron. Here I had applied the step where ANN was just decomposed into neuron. So there are two different steps being applied. Step 4, of course, I'll condense in steps out over here, where multiple steps will be condensed throughout a single step. So what follows are not the actual steps that you would be using when you deal with this problem programmatically. Your for I loop iteration will take in more number of steps than I take it out over here. So let me decompose the first neuron. Let me decompose the first neuron, and let me say that is nothing but a weight W, I'm not writing WEIGHT just to save some bit of space. Else it's WEIGHT weight into some activation function that is constant F into a sum plus bias out here, and this is again W into F into sum plus bias out here. My next step, I decompose this weight, I decompose the sum, I decompose this weight, I decompose the sum, and then decompose these bias. These are the non-terminating symbols out over here. Of course, I'll be doing them all at the same time, what you would not be ideally doing. Let me say this time I do not deal with sum and bias, I only decompose the sum. So it will be W into F into sum. Let me decompose it into sum plus sum. Sum let me decompose here also into sum plus sum. Next step, let me decompose the sum. This sum is nothing but some weight plus bias, and this sum also is some weight and bias. So in this step, let me decompose all these four together. So next step would be W into F into sum would be some weight W again for short form. I'll write down sum W into something from the input list. So let me say I write down IL over here as the INPUTLIST over there. I write down in short form this. It will be again some WEIGHT weight over here and input list over here plus a bias, and this will be WF WL plus WIL plus bias over here. So this what becomes the next step. In my next step, what I'll do is that I'll decompose out all these terms. I'll decompose out W weight, which is nothing but a number. F of weight, which is nothing but a number. My input list is nothing but I1, I2, I3, I4, I5, I6, I7. Let me say that this was I2. Weight, which is nothing but a number. Again, this can be any one of the input. Let me say that is I1 plus bias, which is again a number, plus weight, which is a number into, let's say, I1 plus number into I2 plus bias, which is nothing but a number. In my next step, let me say that evolution of number is something that we would normally not like to deal into. Again, this number of steps would go high with nothing about the neural network being discussed. So let me say there is some mechanism by which I got 0.2, this being replaced by 0.2, this being replaced by 0.7, this being replaced by 0.5, this being replaced by 0.0, this being replaced by 1.0, this being replaced by 1.0, and this being replaced by 0.1. I'll only take one example just to see how they are done. The others would be same. So I take in how can I generate a number from 0.5. I'll say number is nothing but, I change this to number dot number. Number is nothing but a digit list dot digit list. Digit list would be nothing but it can be replaced by a digit out over here and a digit out over here, and a digit can be replaced by 0 out over here and 5 out over here. As per application of same rules, the only thing is that I have selected in rules. So I am able to evolve this neural network using, starting from the ANN, using a set of predefined rules. The choice only lies with how we select the rules, and that is what the genetic algorithm is supposed to do. We specified the grammar, so we started calling it genetic algorithm. That is what the genetic algorithm is supposed to do, generate a mechanism of the right selection of rules. If my genetic algorithm is able to make in a right selection of rules, then this evolution can be complete. Now again, there are time constraints in this entire curriculum, so we will not deal about with an example of how do we take in an genetic individual and do the same thing, and then say that the various numbers over here, which are nothing but set of integers, they can be tuned. This was already done in the earlier session on the grammatical evolution that was dedicated to grammatical evolution. So all those concepts lie the same in how do we carry on. What we've done is first we specified in a grammar, and secondly we verified that any kind of neural network can be generated by this grammar. The only word of caution is that I could have in place of W1 I1 plus W2 I2 over here, I could have got anything. I could have gone W1 some weight into I1 plus some weight again into I1. I could have got only some weight into I1, I could have got only some weight into I2. So it's not possible that my neural network would have an all-connected architecture. My neural network may not have an all-connected architecture. That can be taken for granted. That maybe my neural network in this case is not all-connected. It is some architecture that was shown in the connectionist approach of neural network. Because here I had said that this input gets replaced by I1. Maybe there are some rules are filed in such a way that this gets replaced by I2. Again, it is possible that it gets replaced by W into I1 plus W into I2 plus W into I2 plus W into I2 plus W into I1. All these things are possible in grammatical evolution out of the neural network where we see. The other part that is left for discussion as of now is that once we've got the grammar, how do we generate the individual? The individual is nothing but a random set of integers out over here, a long set of integers out over here. How do I generate this random population is to write down random numbers out over here. This population pool is how it gets generated. How do I convert this genotype into phenotype is what has already been covered into the basics of grammatical evolution, when I have a rule selection mechanism and I keep on exploring the various rules, so I will not repeat that discussion. Genetic operators that we apply, they are all standard: selection, mutation, crossover, elite. So all these would work. It's a linear representation, and the fitness function is nothing but finally I'll get in an equation. Let's say I'll get an ANN as the equation, taking all the various system output. This is what I get as my output. I pass it over to all the inputs in my system. So I pass it over for all I in training database. I note down what the error is, so that will be minus target in input I. And I calculate any kind of error, mean square error, mean absolute square error, root mean square error, percentage error, or anything. I calculate this error, and that is what gets as my fitness. If of course if it's error that I measured out over here, I will not call it as a fitness, I call it as the cost. This is again what we have already seen in genetic algorithms of the where we were trying to evolve the neural network, fixed architecture or the variable architecture neural network. We may add some kind of parsimony. So again, the fitness function will be exactly same as the evolution of variable architecture neural network. It will be exactly the same. And the evolution again will follow the same norms of the grammatical evolution. So that is how using grammatical evolution we are able to end-to-end solve this problem of evolution of a variable architecture neural network. Now, once it gets to evolution of the variable architecture neural network, one thing that we had not seen in the previous session that we left a bit abruptly was the analysis of it. I said that evolution of variable architecture neural network, it will follow the same evolutionary norms where I'll have the fitness of the worst, the best and the average that increase along with generations. This is what I should normally get until they all converge out at the same point. What we had seen was that there was a population of neural networks that we had generated randomly. I call that something as the incremental evolution of neural network. this population of neural network we applied in some genetic operators, which was mutation, crossover. We had some new, we had some insert, there was some grow or whatever. We applied all these out here and generated in a higher generation from the lower generation. And as a result, there were two things happening. Firstly, the number of neurons, they were being optimized, and then the various weights and the biases, they were being optimized. Now, based on whatever we studied, we said that it should follow the same form, that is, for this trend should follow. This is what we ultimately said, that because it's a general evolutionary programming problem, genetic programming, it's a genetic algorithm problem now. Because now it has been reduced to a very general kind of genetic algorithm problem, what ultimately must happen out now, that the curve should be exactly same as we have for the genetic algorithms. So this should be exactly the curve that I get. Apart from the fact that of course the problem is highly computationally expensive, so the generations might be very low. Unlike a general genetic algorithm where the generations are usually very hefty, they are very large in number. So based on that, we do a little bit of discussion over it now. Another view that sometimes you might be interested upon is the error space. So if you are measuring error, this is what you get. Again, the fitness function that we had used there, it was computed as by two means. Firstly, using a performance measure where we had this fitness coming into picture, or an error where we have exactly the opposite curve. This is the worst, this is the best, and this is the average solution. So now there would be another view that I may sometimes make a reference to. Now you imagine out that there exists different spaces, one space for each number of neurons. So there would be a space where there are 10 neurons, there would be a space where there are 20 hidden neurons, there would be a space where there are 15 hidden neurons, and all my various individuals are found somewhere inside the space. All my individuals are to be found somewhere inside this space. So I'm breaking down my entire problem of evolution of neural network, or let me say the incremental evolution of neural network, into two parts. First part says how do you decide the number of neurons, and the second part that says that once this problem has been solved, how do you fix the weights and biases. Those are the two problems that I would be dealing with. How do you decide in number of neurons, and how do you fix the weights and biases? Why did I carry forward this? Because my entire discussion of genetic algorithms, the entire discussion that we took upon in genetic algorithm, it said like that there are there's a fitness landscape, and there are some parameters that you can tune in. So there are some parameters that you can tune in. This forms a base, this forms a fitness function, and based on this you get this. In this case here, the size of the genetic individual is variable. The size of the genetic individual is variable, so this thing cannot be visualized. Some individual has got a 10-dimensional space, some has got a 12-dimensional space, some has, of course, the 10 and 12 are to lesser number, it will be 100-dimensional or 200 dimensions. So this thing is unvisualizable when it comes to incremental evolution of neural network, because the various individuals, they operate in different dimensions of the search space. So sometimes, that's why I break this problem into two parts. The first part says that how do you decide the number of neurons, and the second part says how do you decide the weights and biases. Once the neurons has been decided, then I can visualize this thing out. Once the number of neurons they are fixed, I can decide this thing over up. That what would be the dimensionality of the search space, because the dimensionality would be nothing, the summation of all the weights and biases. So that is what we computed as IH plus HO plus H plus O for the single, for the neural network that we were considering. That once the number of neurons in the hidden layer it has been fixed, then optimize. And that can be done using the evolutionary operators that we discussed. So just for a better visualization, only for the visual part of it, we break this problem into two parts. Now how do I decide the individual? In place of doing that, of course I would not draw out the search space, the fitness landscape. When it comes to the problem of incremental evolution of neural network, I could not draw out the optimization space or the fitness landscape. That's why in place of drawing one landscape, I drew in multiple spaces, all of them with some different dimensions. This is what is the dimensions of the search space. I drew in numerous of them with different dimensions. So if my neurons can vary from 0 to some 25, there would be 25 spaces that I draw out over here. One space for neural network which had only one neuron, the other space for neural network which had only two neurons, the other space for neural network with three neurons. I draw in multiple spaces. In each of these spaces, I can easily draw the fitness landscape because all the parameters are known. All the parameters, they can be nicely tuned. They are no discrete parameters, they are all continuous parameters that can be easily tuned between some minima to maximum. So the individual fitness landscapes can always be plotted. So in this problem, incremental evolution of neural network, what you may sometimes consider only for visual part of it, that in place of drawing one fitness landscape, we are drawing n number of different landscapes where n is the total number of neurons that my evolution can have. I have drawn in 10 landscapes. It could take in 10 as the number of neurons. Each one of these landscapes is conventional in nature, that can be easily plotted in this as a fitness landscape. Now my problem is to select which landscape, and second problem is to decide which point in this landscape. So there are two problems now. Firstly, to discuss whether I need to go here or go here, to select where do I need to go, and inside this where do I need to, which exact point that I am needing. So there are two problems out over here. Deciding the number of neurons, so deciding which one of these landscapes, and fixing the value of weights and biases. So what exact point do I need in this fitness landscape? So what do I do? Initially I place in all, because it's an incremental evolution, so I'll be, let's say this was 10, this was 15 and this was 20. Initially I'll be preferring lower number of individuals out there, I'll be preferring individuals with lower number of neurons initially. So there will be more number of neurons towards the earlier few landscapes and lesser individuals towards the higher few landscapes. That's where this density will be very high over here. All the individuals condense out over here. It's incremental evolution, so these individuals will keep on hopping up towards the lighter side. So as the generations increase, this density would decrease and this density would increase. Still later, this density would decrease and the density would increase. Still later, this density would increase and some other density would increase. This would be the first fundamental that will be governed by the fitness, that will be governed by the number of neurons. The evolution inside this space is all conventional. The mutation operator will apply as it happened with a case of a simple genetic algorithm. The same thing will happen. Of course, there's a local search strategy used. The crossover will behave the same, the mutation will behave the same, the insert of course lies in how do we change in this, how do we add in more individuals and how do we change an individual from low fitness to a higher, from a problem with lower dimensions to a problem with higher dimensions. So they more or less control the distribution of individuals inside these landscapes. They deal with the problem of how do we decide the number of neurons. Mutation crossover aligned all these operators would remain the same when it comes to problems with dealing with how do we converge inside a landscape. I said that crossover would be carried between two individuals with different neurons. So these two individuals can generate the offspring somewhere here. So all this dynamism is possible in this landscape. Again, we can repeat all the operators and see how do they operate in between landscapes and how do we operate inside a landscape. So one thing that was happening was that the individuals keep on migrating from a lower landscape to a higher landscape, a low dimensionality landscape to a higher dimensionality landscape, or from lower neurons to higher neurons. The other is that if 15 is a very good number of neurons, so individuals will generally have high fitness. That's why its density would be reasonably high. This will have a reasonably high density. And not only 15 would have a reasonably high density, 14 and 16 would also have a reasonably high density. And that is what you ideally need to do. In this problem, you need to ideally pair more individuals into the landscapes that are giving me high fitness and lesser ones towards the landscape that are not giving me high fitness. If this general mean is low, I may place very few individuals here. The chances of getting a very high accuracy is poor. But if this general mean is high, I need to place higher number of individuals here. So this distribution of individuals between the landscapes is again attributed by the fitness value. It is again attributed by the fitness value. And the strategy of using various evolutionary operators is that whatever is the number of individuals that I have in hand, I can place them at the better looking landscapes first, and inside this better looking landscape can I place them under better points. So there are two optimizations that they ideally run in parallel. Whenever I talk about the incremental evolution of the neural network, it's kind of two optimizations that are completely running out in parallel. Of course, with a lot of interaction, every operator that we saw out over here had characteristics for both. They had characteristics for selecting the best landscape and characteristics for selecting the best position inside that landscape. Towards the end, what would happen is that there would be essentially convergence where all the individuals would be lying out at the fitness landscape which has optimal number of neurons, and very few would be at other landscapes. Essentially, all the individuals would lie at the same landscape where the fitness is generally high, which is supposed to be the landscape with optimal number of neurons, and then my problem converges to the problem of evolution of a fixed architecture neural network. And the same thing that repeats. Of course, there will be very few individuals that will be trying to explore in regions of high neurons. They would be trying to explore in higher neuron landscapes, but those who can be a small number that you can normally neglect. They would have an effect of these individuals, but again, it would be much lower and that you can sometimes neglect. So this was all about what we did was only for understanding basis is that we saw that how can we do some kind of analysis, how can we better visualize the problem of incremental evolution of neural networks. What lies out to be done? What lies out to be done is that the next problem that we would be dealing is evolution of fuzzy inference systems. All the principles that I took of evolution of artificial neural network, more or less the same are to be applied when it comes to the fuzzy inference systems. So we'll see that how can we just change the neural network part of it towards the fuzzy part of it, and we can have an entirely new hybrid system. Not a hybrid between the neural networks and the evolutionary computing, but a hybrid between fuzzy systems and the genetic algorithms. Again, we'll assume it to be a standard genetic algorithm problem. The mechanism that I took, I'll repeat exactly the same mechanism, so it would be a lot faster. And then we would see how can we evolve fixed architecture and variable architecture fuzzy inference system. So these would be again the two classes that I would be dealing with, and all the models I'll migrate it from neural network to fuzzy inference system. So it will be more of a migration study. How do we migrate between neural network and fuzzy system? So that is what is the agenda. That is what we'll discuss upon the next lecture of the next hour.